about fluids, the number of Reynolds, and planes. Let it go, let it go, let it go. I can't hold it anymore. Okay. So the first thing is that we can ask ourselves the fluid. How can I demonstrate it? I mean, there are lots of fluids. There is like honey that is like very viscous, water that is very fluid. And we can ask ourselves, what the fuck is a fluid? The fluid is a state of matter that is not solid. No, in fact, it means that there is a cohesion between the atoms, that between the molecules that are not strong, not strong, and fluids are very important to know. Like, it's used everywhere. You have lots of fluid for water, for example, oil, everything that has um, pistons, yes, it's like how you say it in English, pistons. And how you do it is you have you study the fluid at a macroscopic scale, so at a mesoscopic scale, sorry. So it's not microscopic because you're not studying it molecule by molecule. You're not studying it macroscopically. So it's not like I say, I throw a box of liquid water to someone. It's like each of the little thingy will happen separately. So mesoscopic will mean that you can define uh, things with small enough so that you can define it, but not big enough so that it doesn't remain true. So what we invented the concept of the particle of fluid. So you'll consider that each of the fluid is one particle and every will behave the same way, but they have special property based on space because there will be like lots of cubes and you can sum them. So we'll obviously have this representation. This is a cube, which is also the particle of fluid. We'll give him, um, um, how we say it, density, that you often call it mu. So it's mass per unit of volume. No, density is it's the thingy compared to water. So it's how compact the thing is in terms of molecules. So yeah, you have this. It's just a cube, and you can put it many things, many letters, as much as you want. You can put mu, which is the how you say it, the molar density, no, the mass, volumic mass. Sorry, I don't know why it get out of my mind. It has a volume, but the volume is mesoscopic, so it's not macroscopic. So you can call it a dV for an elementary volume. It will say that the mu is constant. For example, it's not like you have a lake of honey and a lake of water, and that you are studying both at the same time. I mean, it's really rare, unless you are doing industrial chemicals. But sorry, I'm not going to talk about this. Yeah, so you can put lots of property in it. Then we're going to talk about the speed. The speed, because the speed is very important for knowing how the fluids works. So this is a very important principle of mechanical fluids. When you do that, when you study, you often do this approximation. So you have this box here, that travels through a path in space. You don't know exactly his thingy, but you'll code ligne de I'm just checking my book. Yes. Yeah. In French, the ligne de champ, so the lines that are tangent to the speed, not the trajectory. And you'll do the approximation that the tangent of the speed at a certain moment of the particle of fluid is about the same as the trajectory. You can see on this example, it's not at all the case, because you have the tangent of the speed that is here and the trajectory that is here. But it's really rare that the particle will do a cosine. You don't see, for example, when you put syrup in something, you don't see describing a sine, sorry, it's sine in English. So you don't see it move like that. It's pretty obvious. So what you'll do is do this approximation that the tangent of the speed is about follows the trajectory. Yes, so that's the first approximation you do. Okay, so now this is very important. The fluids follow exactly the same laws as in diffusion of particle, and exactly the same as diffusion of temperature. Weird, isn't it? Well, in fact, there are lots of thingy that relates to it, so I'm not going to demonstrate it, but you can find these laws um, very similar to some things in thermic propagation and propagation of molecules. Okay, so you have the rotational, which is the nabla vectorial, the vector speed v, and this will actually define how the particle rotates. Because you see, for example, if you have a vortex in your bathroom, in your bathtub, where it rotates and then it comes down, you'll have this, which is the vorticity vector, and it expresses how much the particle of fluid will rotate around a um, certain axis. So it's pretty interesting. Usually it's you neglect it, but you have some things where it's not neglectable. Then there is a special property. If this equals 0, the vector 0, then it means that the particle doesn't spin, and it means that you define phi like this one, as being the gradient of v. So you can write v equals gradient of phi. So what it means, you have exactly, just a little parenthesis, you have exactly the same formula for electric potential, and it's exactly the same thing. It's a potential, except that there is a minus, but it's just a convention. Okay, so so you define this thingy that looks like electric potential, and what you do is that you say that there is this thing. This actually is linked with the potential energy, and you call it the potential, but I'm not going to give too much details about it. Okay, so now imagine all the people thingy, de son, de signe de son. Okay, not saying too much bullshit. Okay, so I'm reading my book. I'm cheating here. In a viscous fluid, there is more of the force of cisaillement or viscosity in the fluid. For a one-dimensional x-based movement with a gradient following the y direction, the law of Newton giving the elementary force of viscosity that a particle of fluid between y and y plus dy, so that's just the case where we have our particle of fluid going in one direction, so to the x direction, so you have the x direction, and you have upward the y direction. And you want to know the force between this particle and the particle, and the force that this one applies on the particle below it. So yeah, so this force, yeah, okay, so you'll actually find this formula. So what it means is that with this being the x-axis, it means that the particle, when it moves, it slightly pushes, it brings a bit the particle below it. So the one is going at a certain speed, and it drags a bit. It says, go, do your thing, do your thingy, and it pushes slightly, but not entirely. And also, just to remind, if they go to the same speed, you can give the approximation that it's a non-viscous fluid. So okay, so we have defined viscosity. Yeah, so by definition, eta is the viscosity. That's how you define it. ds is the elementary surface between the two particle of fluids. The differential of v on y, it means that the speed between on the y-axis. I think it's a mistake. It's actually x. Yeah, I think there is a mistake in my book. Yeah, there is a mistake in my book. Fuck. Yeah, because if you derivate it by x, you can't find the function of y. Yeah, it's x and function of y, and there is a mistake in my book. Fuck my book. Fucking French flags. Okay. So it's the dynamic viscosity eta. Okay. Now, there are two formulas. The Stokes formula for low speed, for particles that are going slowly, very slow, and a formula for fast speed. So for fluids that do ABH over GU. The formula of ABH over GU, exactly. So this formula here, the formula of Stokes, F equal minus 6 pi R V, and on the direction V. So yeah, what it means is that F is equals to minus 6 pi. So this comes from the fact that you consider, oh no, I'm not going to talk about it, but you have this minus 6 eta R. Also, I think I forgot R, the eta. Okay. Times R V times EV. So the direction of the speed. So it just means that the viscosity will drag the thing with it. It's not the same as this one, but you just integrate it on special surfaces. See, this one is very common. And for fast speed, you have this F equals minus 1/2 of Cx mu, where mu is the volumic mass, pi to the direction of speed. And I think I forgot about I forgot about the v squared. There's the v squared. Sorry. Okay, you have it. You have it. What's Cx? Cx is just a constant that you are usually given in the exercises. It's measured by a few laboratories. It depends. Okay, now the number of Reynolds. Okay, I have to say something very important. So real talk, real talk, real talk. The sorry, the number of Reynolds is not a number. It can seem weird, but it's an approximation in terms of power of 10. So it's not a number like exactly a number, it's circa a number. So for example, if you are moving at 100 kilometer 101 kilometer per hour, it's circa the same as if you were moving at 100 kilometer per hour. So you'll approximate everything, and that will give you circa the good thing, but it's not a real calculus, that there is not one number of Reynolds per volumic per fluid. It's not a constant, it's not something like that, it's something that you approximate. Okay, let's go back. So the number of Reynolds, yeah, thanks. The number of Reynolds is defined like this: RE equals mu LV divided by eta, where mu is the volumic mass, eta the dynamic viscosity. What's L and V? L is it's the approximation that you give of the length of the surface that touches the thing that you consider. For example, if it goes one way, then you have something that touches it. Yeah, okay. For example, if you have on your bathroom the thingy where the fluid comes out, the diameter will be the L. It's not very important the exact value. It's usually in centimeters, but it matters of your system. And V is an approximation of the speed of your fluid. And, as I wrote, the limit is 200. 2000, sorry, 2000. 2000. It's not a law. It's something that has been calculated experimentally. So you put a fluid and you to study how it works. So at circa 2000, what happens is that below you'll have let's switch scene. Below you have a fluid that works like if they didn't know the particle of fluid that is below it. That like if it isn't as being non-viscous. Yeah, no, as being what am I saying? Yeah, as being laminary, meaning that you can approximate. I'm going to do a graph. Okay, sorry, I was confused by my own self. Okay, so it means that you can consider the fluids as being lines on a certain dimension of space, and that you can study each of the lines separately. So that's if the number of Reynolds is inferior to 2000, but there is another case where you have to what will happen is that there will start to be vorticity, which means that there is rotations between in your system. So it means that the system will not be straight. Oh shit, not like this. It will start to do weird stuff like this. No, maybe it's too exaggerated, but it will start to do like this. I mean, it will not be straight, and the thingy will start to have rotations on it. It's what happens in planes, for example. Yeah. So with a laminary study, so Reynolds inferior to 2000, it means that you have a one direction. It means that you have the top that drags the bottom one with a certain force at a certain speed, and this one will drag the one below itself with another force, which will drag the other below itself. Okay, and what will happen is that there is obviously a layer where this is not true. You can't consider that there is speed anymore. Yeah, where viscosity is bad, and the trajectory is the speed is circa constant, because this will be really low. So it's called the limit layer. You call it delta because it's exactly the same as electromagnetic wave, and I'm really sure about that. It's L divided by the square root of the Reynolds number. So at this layer, you will say that this is, after this, all are the same length. All are the same length. All the vectors are the same length on delta, with this being delta. Okay. For turbulent, there are no laws because it's too hard to study, and actually there are no formula for this. You have to study each of the fluids independently. Okay, now I'm going to talk about planes. I took my book. Okay, so you have the force, you have your plane. Okay, I'm going to do, well, the future. You have your plane like this, and there are obviously forces that comes from the air. So obviously you can't study, when you're a pilot, you can't study each of the particle of fluid that happens to to collide with the plane. It's trivial. You have to do another study. You'll consider that the forces that you consider the plane. So imagine it's a plane. So I decay how to do a plane, but you do a plane, and you consider the forces that exerted by the air, the air on the plane. So what will happen is that you will define r as being this. So it has two components on the x. So the fact that the air just pushes backwards the plane, and the fact that it pushes upwards if you put the air, it pushes upward the plane, and I said 0 on the y-axis because theoretically it's 0, but there is spin. Obviously, if there is air and that it's different from one week to another, it's going to spin the thing. If you have the air that comes front, and if it's more important on one of the side, it will start to spin, and there will be a movement of spin, of rotation, yes, spin. Yeah, so it's this formula: 1/2 of mu, where mu is the volumic mass. S is the surface of meat, where not meat like the ham, meat like the surface where hair meet the plane. Obviously, it's not going to meet on the back. Okay, it's times v squared times cx, where cx is a constant given by the builder or whoever wants to, and same for cz. Okay, now we have done that. Usually cx and cz are functions of alpha, the angle between the angle of the plane, because obviously if the plane is like this, it's not the same as if the plane was like this, and if the air comes like this, it's going to push it backwards, and if the air is like this, it's going to push it upwards. So often this is Cx and Cz are functions of alpha, and that's how you study it. Yeah, that's pretty much it. There are lots of effects that happens with few things, like for okay, to be serious about this, to be very serious. So imagine this is a plane. I'm going to show it sideways. So you'll have the air that comes from this side, and there will start to be depressure here on the wings. So what you will have is small parts that are fixed on the wings of the plane, that will start to modify the turbulence, the fact that the number of Reynolds, number of Reynolds, in a way that the spins that are in the particle of fluid will actually be better for the path of the plane, which is why it's very complex, because you don't know where to put it in the wings of the plane. So you have to study it and study how it will modify, and also you can modify the angle. So it's very complex, and yeah. So yeah, thanks for watching, and bye.